Picture the Sahara, the way most people picture it. An endless, lifeless sweep of golden dunes stretching from the Atlantic coast of Morocco all the way to the banks of the Nile, the largest hot desert on the entire planet, roughly the size of the continental United States. A place so dry that some weather stations inside it have gone years without recording a single drop of rain. Now picture something almost impossible to reconcile with that image. An ocean's worth of water sitting directly beneath your feet the entire time, locked away in the rock, quietly waiting there for tens of thousands of years, while the surface above it turned into the driest, harshest landscape on Earth. That's not a metaphor, and it's not an exaggeration dreamed up for a headline. It's the literal, scientifically documented reality of what lies underneath the Sahara, and understanding exactly how it got there, what it actually is, and why it matters right now is one of the more genuinely mind-bending stories in modern Earth science. By the time we're finished here, you'll understand exactly what this hidden reservoir is, how it formed, why it's been sitting there so long without anyone touching it, what's already being done with it, and why the discovery carries consequences that stretch from rural farming communities all the way to geopolitical tension between entire nations. Let's start with the basic shape of the story, because the discovery itself unfolded gradually over decades, rather than in a single dramatic moment, which is part of why it took so long for the wider public to fully grasp the scale of what scientists were actually finding. Beginning in the mid-20th century, geologists working across North Africa, drilling for oil and conducting geological surveys, kept encountering something they didn't initially expect deep beneath the desert floor. Layers of porous sandstone completely saturated with fresh water, sitting thousands of feet down, far beneath any surface hint that water existed there at all. As more wells were drilled and more seismic surveys conducted across Libya, Egypt, Chad, and Sudan, a clearer picture started to emerge. This wasn't a small, isolated pocket of trapped moisture. It was an absolutely enormous, interconnected system of water bearing rock stretching across an area of more than 2 million square kilometers, a footprint large enough to blanket the entire country of Mexico and still have room left over. Scientists eventually gave this system a formal name, the Nubian Sandstone Aquifer System, and today it's recognized by international bodies, including the International Atomic Energy Agency, as the largest known fossil water aquifer system anywhere on the planet. Here's where the numbers involved genuinely start to feel unreal, and it's worth taking a moment to actually sit with the scale rather than let it wash past as just another impressive sounding statistic. Researchers estimate the total volume of water held within the Nubian Sandstone System alone is roughly equivalent to about 500 years worth of the entire Nile River's discharge, and separately, it's been described as holding a volume of water about 20 times larger than all 5 of North America's Great Lakes combined. And that's just one aquifer system, albeit the largest and most famous one. Further west, an entirely separate formation called the Northwestern Sahara Aquifer System stretches beneath Algeria, Tunisia, and Libya, and additional major basins have been mapped beneath the western and central stretches of the desert as well. When the British Geological Survey, working alongside researchers from University College London, conducted a continent-wide assessment of Africa's total groundwater reserves, they arrived at a truly staggering figure. Roughly 500,000 cubic kilometers of water sitting beneath the African continent as a whole, an amount equivalent to more than 20 times the volume of water that falls across the entire continent as rainfall in a typical year. The lead geologist behind that assessment noted that the volume held underground dwarfs what's visible on the surface by roughly 100 times over. A genuinely staggering ratio that helps explain exactly why the phrase, "an ocean beneath the desert," isn't hyperbole. It's a reasonably fair shorthand for the sheer scale involved, even if it's worth being precise about what that phrase does and doesn't actually mean physically. It's worth pausing on how researchers even arrive at numbers this large, because measuring something you can't see or directly walk through requires a genuinely clever combination of techniques layered on top of each other. Seismic surveys, the same underlying technology oil companies use to hunt for underground reserves, allow geologists to essentially bounce sound waves down through the crust and read back the resulting echoes to map the depth, thickness, and boundaries of porous rock layers likely to hold water, all without ever needing to drill a single exploratory well. That broad picture then gets refined and calibrated through actual deep drilling at carefully chosen locations. Direct physical confirmation that ties the seismic estimates to real, measured water-bearing rock. In North Africa specifically, researchers found something that genuinely surprised them during this process. Pockets of stored water sitting roughly 75 meters thick in places, protected from above by unusually hard, dense rock layers like granite, a combination that had helped keep this reservoir remarkably well sealed and largely undisturbed for an extraordinarily long stretch of geological time, right up until modern drilling technology finally became capable of reaching down far enough to tap into it directly. Estimating a continent scale figure like the 500,000 cubic kilometer total also comes with real scientific uncertainty attached. And it's worth being upfront about that, rather than presenting a single number as though it were settled beyond any doubt. A separate, widely cited, continent-wide assessment published in the academic journal Environmental Research Letters back in 2012 arrived at a broadly similar estimate of around 660,000 cubic kilometers of groundwater held across Africa, but attached a genuinely wide uncertainty range to that figure, anywhere from roughly 360,000 up to as much as 1.75 million cubic kilometers, depending on the specific assumptions and modeling techniques applied to different regions across such an enormous and geologically varied continent. That range might sound uncomfortably imprecise for something described so confidently in headlines, but it's actually a fairly honest reflection of just how difficult it is to measure a resource hidden thousands of feet underground across millions of square kilometers of remote, difficult-to-access terrain, and even the most conservative end of that uncertainty range still represents an absolutely enormous volume of water by any reasonable standard. And that precision matters, because it's the exact point where popular explanations of this discovery tend to drift into something a little more mythical than the actual geology supports. So let's be genuinely careful here. There is no single underground sea beneath the Sahara, no vast hollow cavern filled with water, the way you might picture an actual ocean basin, sitting there like some enormous hidden swimming pool waiting to be tapped. What actually exists is water occupying the tiny connected pores and fractures running through sandstone and other porous rock formations, the exact same way water saturates a sponge rather than sitting in an open chamber. Exactly the kind of clarification the United States Geological Survey offers whenever this discovery gets discussed publicly. That distinction genuinely doesn't make the discovery any less remarkable. If anything, it makes the actual physics considerably more interesting, because it means this water has been slowly percolating through solid rock at a molecular scale for an almost unimaginable length of time, filtered and purified in the process by the very sandstone that's been holding it in place ever since. Layered on top of that clarification is another one worth understanding. The age of this water isn't a single tidy number either. Different samples drawn from different depths and different locations across the aquifer system record entirely different recharge episodes, some water dating back tens of thousands of years, while water pulled from the deepest portions of the Nubian aquifer has been dated to hundreds of thousands of years old, with some estimates for the very oldest layers approaching nearly a full million years. In other words, this isn't a single ancient rainstorm frozen in time beneath the sand. It's a layered geological archive, a record of repeated wet periods stacked one on top of another, going back an extraordinarily long way, each layer representing its own distinct chapter in the desert's deep climate history. Which brings us directly to the central question this entire discovery revolves around, and it's genuinely one of the more fascinating pieces of climate science to come out of the last several decades. How did an ocean's worth of fresh water end up trapped beneath what is today the driest, most hostile desert landscape on the planet? The answer lies in something scientists call the African humid period, sometimes referred to more simply as the Green Sahara, and understanding it requires zooming out to appreciate just how dramatically different this landscape looked for large stretches of its deep history. The most recent and best documented of these green phases ran roughly from 11,000 years ago to about 5,000 years ago, a span during which the region we now call the Sahara was, almost unbelievably, covered in grasslands, wooded savanna, sprawling wetlands, and numerous freshwater lakes. This wasn't a marginal, barely habitable fringe environment either. Archaeological and fossil evidence from this period shows fish, crocodiles, and hippopotamuses living in places that today rank among the most punishingly arid stretches of ground anywhere on Earth, alongside extensive evidence of early human communities that settled directly beside those ancient lakes and rivers, building entire ways of life around a landscape of abundant water that has since vanished almost completely from both the surface and from popular memory. The mechanism driving this dramatic transformation, and driving its equally dramatic reversal, comes down to something happening nowhere near the Sahara at all, deep within the physics of Earth's own orbit around the Sun. Our planet doesn't spin on a perfectly fixed axis. It wobbles slowly over time in a process astronomers call precession, similar to the way a spinning top gradually tilts and rotates around its own axis as it slows down, and that wobble cycles through a complete rotation roughly every 19 to 23,000 years, a span scientists generally round off to about 21,000 years as a working shorthand. During certain phases of that slow wobble, the northern hemisphere ends up positioned closer to the sun during its summer months, intensifying the strength of the seasons, and crucially for this story, dramatically strengthening the West African monsoon system, driving significantly more rainfall deeper into what is today the Sahara than the region receives now. Once that rain started falling in earnest, a set of powerful feedback loops kicked in and amplified the effect considerably beyond what the orbital shift alone would have produced. Newly established vegetation reflects far less sunlight back into space than bare, pale desert sand does, which means more solar energy gets absorbed at ground level, further intensifying the atmospheric conditions that support rainfall. Vegetated soil also retains considerably more moisture than exposed sand, and crucially, a green, vegetated landscape kicks up dramatically less atmospheric dust than a bare desert does, and that reduction in airborne dust allows even more sunlight to reach the surface and further reinforce the emerging monsoon pattern. Put together, these reinforcing feedback loops turned what began as a fairly modest orbital nudge into a landscape-wide transformation, an entire desert flipping into savanna and wetland for thousands of years at a stretch. Researchers using sophisticated coupled climate models have been able to reconstruct this cycle with remarkable precision, running detailed simulations covering roughly the past 800,000 years of Earth's history and successfully reproducing something like 20 separate instances of North Africa, cycling through these humid green phases, each one matching up closely with humid intervals, already identified independently through geological evidence like ancient lake sediments and fossil pollen records. Those simulations also revealed an important wrinkle in the pattern. This precession-driven greening didn't happen with perfect clockwork regularity every single cycle, because Earth's orbital eccentricity and, even more significantly, the presence of large ice sheets covering the high latitudes of the northern hemisphere during full glacial periods actively suppressed the greening effect during certain windows, even when the underlying orbital precession would otherwise have favored a wetter Sahara. Essentially, the orbital wobble supplies the rhythmic pacing for this entire cycle, functioning almost like a metronome ticking away in the background of deep time. But the broader climate system, oceans, ice sheets, vegetation feedback, and atmospheric dust, all interacting together, determines how strongly North Africa actually responds to that underlying beat during any given cycle. It's a genuinely elegant piece of climate science, tracing a chain of cause and effect that starts with the subtle wobble of a planet spinning through space and ends, tens of thousands of years later, with fish and hippopotamuses living where sand dunes now stretch to the horizon. Then, roughly 5,000 years ago, that green window closed, and it closed with a swiftness that has genuinely surprised researchers who've studied the transition in detail. As the orbital precession cycle continued its slow rotation, the intensified summer monsoon that had been sustaining the Green Sahara gradually weakened. And once rainfall dropped below a critical threshold, the same feedback loops that had amplified the wet phase flipped into reverse and began amplifying the dry phase instead. Vegetation died back. Exposed soil and sand reflected more sunlight and generated more atmospheric dust, and the whole system tipped rapidly toward the hyper-arid desert landscape recognizable today. Detailed sediment records pulled from ancient lake basins in East Africa have allowed scientists to study this transition with a level of resolution most paleoclimate research simply doesn't have access to. And what that fine-grained record shows is a period of pronounced climate instability lasting roughly 1,000 years, marked by repeated droughts recurring every century or two, interspersed with occasional bursts of extreme wetness, a kind of climatic flickering back and forth before conditions finally settled into the stable, arid state that has now persisted for the past several thousand years. Throughout that entire multi-thousand-year humid period, and especially through its later wetter phases, rain falling across the region didn't just support surface lakes and rivers, it steadily seeped downward through porous rock layers, slowly recharging the deep sandstone aquifers below, filling them layer by layer over thousands of years, the same way filling a giant underground sponge would work, drop by drop, century by century. And then, once the rain stopped and the surface transformed into desert, that water simply had nowhere left to go. Sealed beneath layers of rock and sediment, protected in places by extremely hard, largely impermeable formations like granite that keep the reservoir contained, that ancient rainfall has simply been sitting there ever since, essentially frozen in geological time, completely disconnected from the modern rainfall cycle above it. Scientists refer to water trapped under these conditions as fossil water, a term deliberately chosen to echo the way fossil fuels represent an ancient, finite resource laid down under conditions that simply no longer exist at the surface. Water that isn't being meaningfully replenished today, no matter how much rain might occasionally fall on the modern desert surface above it. That finite, non-renewable nature is precisely what makes the modern human relationship with this ancient water source such a genuinely complicated and consequential story. And nowhere has that story played out more dramatically than in Libya. In the early 1980s, Libya's government announced an almost unbelievably ambitious engineering project, one that was publicly described at the time as the eighth wonder of the world, an enormous network of underground pipelines designed to pump fossil water up from deep wells drilled into the southern Sahara and carry it more than 1,000 miles north to supply the country's densely populated coastal cities. Construction stretched across more than 2 decades, and the finished infrastructure, widely referred to as the Great Man-Made River, remains recognized as the largest irrigation and water transport project ever constructed by human civilization, roughly 4,000 kilometers of massive underground pipes carrying water that, in some cases, fell as rain during the depths of the last ice age, tens of thousands of years before a single stone of the pipeline itself was ever laid. Cities that would otherwise sit in one of the most water-scarce environments on the planet have depended heavily on this ancient underground reserve for drinking water and agricultural irrigation for decades now, transforming portions of the landscape and supporting millions of people who would otherwise have essentially no reliable local water source at all. But there's an uncomfortable mathematical reality sitting underneath that engineering triumph, and it's the exact tension that makes this story so much more than just an impressive feat of infrastructure. Because this water isn't being replenished by any meaningful modern rainfall, every single drop pumped up out of those wells and sent north through the pipeline network represents a permanent withdrawal from a fixed ancient reserve, precisely analogous to pumping oil out of the ground, an irreplaceable resource being drawn down rather than a renewable one being sustainably managed. Researchers who've studied extraction rates against the total estimated volume of accessible water have offered projections suggesting the aquifer, at current rates of use, could continue supplying water somewhere in the range of 60 to 100 years before reserves in the most heavily tapped regions become significantly depleted or increasingly difficult and expensive to access. That estimate carries real uncertainty attached to it, though, and other researchers studying the same system have specifically cautioned that depletion could accelerate considerably faster than that range suggests if neighboring countries sharing the same underground reservoir significantly ramp up their own extraction simultaneously. A genuinely realistic possibility given how many nations sit directly above the same interconnected system of rock and ancient water. The scale of the great man-made river project itself is worth understanding in a bit more physical detail too, because the engineering challenge involved genuinely rivals some of the more famous infrastructure projects built anywhere on Earth. The wells feeding the network reach down through well over 500 boreholes drilled deep into the desert floor across Libya's southern reaches, drawing water that then flows northward through massive precast concrete pipes, some of them wide enough for a small vehicle to drive through, buried beneath the desert and connected across a distance comparable to traveling from New York City to Denver. Financing and constructing a project on that scale took decades and an enormous share of the country's oil revenue during the years it was built, and it stands today as a genuinely rare example of a nation investing overwhelming resources into solving a water scarcity problem through direct extraction of an ancient underground reserve, rather than through the more commonly used approaches elsewhere in the world, like large-scale desalination of seawater or extensive water recycling infrastructure, both of which carry their own very different sets of costs, energy requirements, and long-term trade-offs. And that shared geography is really the crux of why this discovery carries implications reaching well beyond hydrology and into the realm of international relations. The Nubian Sandstone Aquifer System doesn't respect national borders in the slightest. It stretches directly beneath Libya, Egypt, Chad, and Sudan simultaneously, meaning a well drilled and heavily pumped on one side of a national boundary can measurably affect water pressure and long-term availability for wells drilled on the other side of that same boundary, sometimes hundreds of miles away. That reality has pushed international organizations, including the International Atomic Energy Agency, working alongside regional governments to develop specialized scientific techniques specifically aimed at managing this shared resource responsibly. Among them, a method called isotope hydrology, which allows researchers to essentially read a chemical fingerprint embedded within water samples pulled from different wells, helping to determine how old a particular pocket of water actually is, how it's moving through the underground rock formation over time, and crucially, how withdrawal in one location is likely to affect availability elsewhere across the shared system. That kind of careful cooperative monitoring exists precisely because water, this valuable, this ancient, and this finite, has the very real potential to become a genuine source of tension between nations if extraction isn't managed with a level of coordination and transparency that, frankly, hasn't always been easy to achieve in a region that has faced its own share of political instability and competing national interests over the decades. This aquifer has been actively tapped. It's also worth pulling back from Libya specifically and looking at what this broader category of discovery means for the African continent as a whole, because the implications here reach directly into one of the most pressing humanitarian challenges facing the region today. Hundreds of millions of people across Africa currently lack reliable access to safe drinking water, and the same geological survey that mapped the continent's total groundwater reserves specifically highlighted just how transformative these deep aquifer systems could be if developed thoughtfully and sustainably, potentially offering a meaningful path toward improved water security for tens of millions of people, alongside considerable potential to boost agricultural productivity in regions where surface water has always been scarce or entirely absent. Beyond the Sahara itself, researchers have identified other major underground reserves scattered across the continent, including substantial basins along the coastlines of Mauritania, Senegal, Gambia, and parts of Guinea-Bissau, as well as significant formations found in the Congo Basin and along the border region shared by Zambia, Angola, Namibia, and Botswana. Smaller, more localized aquifer systems have proven genuinely transformative on the ground already. In Niger, for example, the Irhazer-Ilumidane Basin. Aquifer has become a critical water source for communities in one of the hottest, driest countries on the planet, with wells drilled into that specific formation directly improving access to clean water, supporting small local economies, and freeing up time that would otherwise be spent on the exhausting, often dangerous daily task of traveling long distances simply to find drinkable water. It's worth being clear, though, that drilling a well into a formation like this is rarely as simple as sinking a pipe into the ground and letting water flow. The terrain across much of the Sahel and the deeper Sahara itself tends to be rocky, remote, and genuinely difficult to reach with heavy drilling equipment, meaning even a single successful well often represents a significant logistical undertaking. Transporting machinery over long distances across terrain with little to no existing infrastructure, before the actual drilling process, which itself demands real precision to avoid damaging the surrounding rock formation or compromising the long-term integrity of the well itself, can even begin. And that difficulty compounds the underlying inequality already present in how access to this ancient resource gets distributed. Wealthier nations with established oil and gas industries, like Libya, already possessed much of the technical expertise and heavy equipment needed to exploit these deep formations at scale, while some of the poorer nations, sitting above the exact same shared aquifer systems, have historically lacked the resources to tap into that same underground wealth nearly as effectively. An imbalance that adds yet another layer of complexity to the already difficult question of how a resource, this valuable, this ancient, and this unevenly distributed, in terms of who can actually access it, ought to be managed fairly across an entire region. That said, the genuine promise of these aquifer systems comes bundled with real, sobering limitations that deserve just as much attention as the impressive headline numbers, because treating this discovery as some kind of simple and limited solution to water scarcity would badly misrepresent the actual science. These reservoirs are, by definition, finite resources being drawn down rather than naturally replenished at any meaningful pace, and drilling into them, particularly at the depths involved in the Nubian Sandstone System, requires genuinely serious engineering capacity, sustained financial investment, and careful long-term planning that many of the communities who would benefit most from this water simply don't currently have consistent access to. There's also a real ecological dimension worth considering, because even fossil water reserves that sit disconnected from the modern surface water cycle can still be connected, in subtler ways, to surface ecosystems and to smaller, shallower aquifers that communities have relied on for generations, meaning poorly planned excessive extraction from deep wells has the potential to inadvertently affect water availability in shallower systems nearby, an unintended consequence that underscores exactly why the kind of careful scientific monitoring described earlier isn't just a bureaucratic formality. It's a genuine safeguard against repeating, on a larger and more consequential scale, the same story of rapid depletion that has already played out with heavily drawn down aquifers in other parts of the world. There's a useful comparison worth drawing here to other heavily exploited fossil aquifers elsewhere on the planet, because the Sahara's situation, while enormous in scale, is far from a unique case study in how humanity manages ancient underground water. The Ogallala Aquifer underlying much of the central United States, a reservoir that similarly formed over an extraordinarily long geological timescale and similarly receives only a small fraction of meaningful modern recharge in many of its regions, has already experienced significant measurable depletion in some of its most heavily farmed areas after decades of intensive agricultural pumping, with water tables in certain counties dropping by well over 100 feet since large-scale irrigation began there in the mid-20th century. That real-world precedent offers a genuinely sobering preview of what unmanaged, unrestrained extraction from a fossil aquifer can eventually look like over a long enough timeline, and it's precisely the kind of cautionary example that researchers and policymakers studying the Nubian Sandstone System point to when arguing for careful, internationally coordinated management, rather than treating this newly appreciated Saharan reserve as an inexhaustible resource, simply waiting to be tapped as aggressively as engineering capacity allows. It's also worth noting how this specific discovery fits into a much broader pattern researchers have increasingly documented across arid regions worldwide, ancient, disconnected reservoirs of fossil water sitting beneath modern deserts on nearly every continent, remnants of climate conditions that vanished from the surface many thousands of years ago. Similar fossil aquifer systems have been identified beneath portions of the Arabian Peninsula, parts of the Australian outback, and stretches of the American Southwest, each one representing its own distinct chapter of ancient wetter climate, locked away beneath a landscape that today bears no visible resemblance to the conditions that originally filled it. Taken together, these scattered discoveries paint a genuinely striking picture of just how much of Earth's deep climate history remains quite literally hidden beneath our feet, an invisible archive of ancient rainfall patterns, vanished lakes, and long extinct ecosystems, still measurably present and, in a growing number of cases, actively shaping the water, security, and geopolitical relationships of the modern communities living directly above them. Stepping back from the individual details, what makes this entire discovery so genuinely remarkable isn't just the staggering scale of water involved, though that scale alone is worth sitting with. It's what the whole story reveals about how dramatically Earth's climate has shifted over spans of time that dwarf the entirety of recorded human history, and how directly those ancient shifts continue shaping life on the surface today, tens of thousands of years after the rain that created this reservoir last fell from the sky. A desert that appears permanent and unchanging to anyone standing in it today was, for thousands of years at a stretch, repeated over and over across hundreds of thousands of years. A landscape of lakes, rivers, grassland, and thriving human communities. And the physical evidence of that transformation isn't some faded historical footnote. It's an active, measurable resource sitting directly beneath the modern desert surface, quietly waiting there, being tapped, studied, and in some places responsibly managed, while in others drawn down at a pace that raises real questions about what comes next once those ancient reserves eventually run dry. Understanding that history also offers a genuinely useful lens for thinking about the future too, because the same orbital mechanics responsible for greening the Sahara repeatedly across deep time haven't stopped operating, meaning the planet's slow orbital wobble will, over a time scale of many thousands of years, eventually push conditions back toward another green phase in this exact region. A reminder that even the most seemingly permanent features of our planet's geography are really just the current chapter in an extraordinarily long, cyclical story still very much being written. If a story like this one, connecting the physics of Earth's orbit all the way down to the water coming out of a tap in a Libyan coastal city, is the kind of deep dive you find genuinely worthwhile, hitting like helps more people come across it, and if you've got thoughts on how a resource this ancient and this finite should be managed, or if you're curious about other hidden reservoirs like this one scattered across the rest of the planet, dropping a comment adds exactly the kind of perspective a video like this can't offer on its own. Subscribing means you won't miss the next deep dive into a discovery like this one, because the more researchers study Earth's deep geological and climate history, the more of these genuinely surprising stories keep surfacing. And if you know anyone who'd find the idea of an ocean's worth of water hidden beneath the world's largest desert as fascinating as it clearly deserves to be, sharing this along costs nothing and might just change the way they think about deserts and about deep time itself for good.